we can do substitution reactions where we replace hydrogen with halides using radical reactions. What we're going to do is replace the hydroxyls of alcohols with halides. So we're going to turn an alcohol into an alkyl halide. And there's two mechanisms for these substitution reactions. The first one, it's called an SN1 reaction. We're going to spend a lot of time talking about these things, but you can see what you do is you take the hydroxyl group and you replace it with the halogen, right? Hydroxyl leaves. The mechanism is this. So this is my nucleophile. The lone pairs on O attacks H, like we've seen with alkenes, right? Same thing. Goes there, that goes there. Then what we get is this activated alcohol. So now this O is making 3 bonds. It doesn't want to do that. It's unhappy. And here, this is a nucleophile, right? It's not electrophilic on O. What happens here is that this O wants those electrons. So he takes this pair of electrons and leaves. And what you get is a carbocation plus water. And then in the last step, the bromide that we made in the first step adds. Right, and the reactivity of the alcohols is that methanol is the least reactive, primary are a little more reactive, secondary getting better, tertiary are the best. Basically, using this mechanism, secondary and tertiary are the ones that we look at. And the reason is this carbocation intermediate that we make, right? This guy is, well, we know the rules about carbocations, carbocation stability, right? So this guy, tertiary is the most stable. So in this slow rate-limiting step, right, we form a carbocation. Anything that's going to stabilize that, right? This is an endothermic reaction. So the tertiary would be here, the secondary would be here, right? Hammond's postulate allows us to predict that these transition states will be similar to those carbocations. So the more stable carbocation is more quickly formed. All right, try to do this one more time. So we need to recognize that if you treat this with an acid, HBr, HCl, or HI, HCl sometimes needs a catalyst, but we'll just say it works. You're just going to do a substitution reaction and lose water. Again, this mechanism we want to be able to draw 2 steps. First step, you protonate to make the water a better leaving group. Right, this O wants those electrons now, takes them. This is the slow step, right? The rate-limiting step is the formation of the carbocation intermediate. And then finally, chloride adds, and we get our product. All right, so this mechanism is called SN1. And it's a really fundamental reaction in organic chemistry. So SN1 stands for substitution nucleophilic unimolecular. Let's just take a look at this. So the rate limiting step, right, we can write a rate law for that, right? Rate equals K times, the general form, you remember, is rate equals K times A to the M times B, the concentration of B to the N, right? Where these are the orders of reaction, right? If the order is 1, if it's first order, that means 1 thing is required in the rate limiting step. If it's second order, it means that 2 things are smashing into each other. This reaction is first order in, this substrate. We'll call this guy the substrate, right? You can abbreviate it as Rx, right? Something with, we'll just call that the substrate. So it's first order. This is the rate limiting step, and this one determines the rate of the reaction, right? It's a 2-step reaction. So you form the carbocation first, and then you do addition. Really important to remember, there's a carbocation intermediate, and you get a racemic mixture of products. And why is that? Because the carbocation intermediate, when that nucleophile adds to the planar carbocation, it can add from the top or the bottom, giving you both enantiomers if it's chiral. Right? These are all things you need to know about SN1 reactions. The other kind of reaction is best for primary and secondary, although it works for tertiary. It's called an SN2 reaction. And so substitution, nucleophilic, and it's bimolecular or second order. And so the same thing happens. It's a substitution reaction. I'm replacing the alcohol with a halogen, right? I still have the same number of carbons. We don't change those. And what's happening here for phosphorus tribromide or thionyl chloride, what these guys do is do the same thing as the proton in the first reaction. The acid activates that leaving group, so it is better able to leave. So you want to recognize that primary, secondary, and tertiary alcohols with PBr3 will give you the alkyl halide. I'm not really interested in the other products, but this is the most important thing. Thionyl chloride is this one, and it looks like this. Whoa, what am I doing here? Okay, got this. Nope, I'm not doing it. Thionyl chloride looks like this. So the alcohol is still the nucleophile in the first step, but instead of attacking, this guy's going to leave. O-S, double bond, Cl, there, and Cl minus. Oh, plus H plus. This is a catastrophe, isn't it? The second step, well, yes. So this is called pyridine, and it's a weak base. Bases are Bronsted. Bronsted bases are proton acceptors, so he's going to grab that proton from the O. So Cl minus is still floating around, and now we've got pyridinium, the protonated form of this guy. All right, so this sets up the final product, right? What we've done is we've activated our alcohol, right? This O was a hydroxyl group, it doesn't want to leave, right? It has a very strong bond between O and C. Over here, we protonated it to make it a better leaving group. Here, we're activating it by forming this bond with the rest of the molecule. So it's the same theme, we're activating O. And now what happens in the rate-limiting step here, one step, chloride attacks, these electrons push over, that guy leaves, and we get all our products. And so important things to recognize here are, this is called an SN2 reaction. This step is actually the SN2 step. What you have is the rate law depends on both the substrate and the nucleophile. That means that the substrate, this guy, right, and the nucleophile have to smash into each other for this reaction to go. And that's the slow rate limiting step. And that's what this rate law describes. So it's first order in both the substrate and the nucleophile. And so if I doubled the concentration of the nucleophile, we would expect the rate to double. If we doubled the concentration of the substrate, we expect the rate to double. If I doubled both, I would expect the rate to increase by 4, right? It's a single step reaction in this SN2. And we say it involves backside attack and inversion of stereochemistry. So let me draw another picture here. So let's say we've got this guy, just methyl, and I'm going to put a bromide there, methyl bromide, and I'm going to use, so you can use this SN2 reaction with a lot of different substrates. Here we turned an alcohol into an alkyl halide. Here I'm going to do the opposite. I'm going to turn the alkyl halide into the alcohol. But the important thing here is, I'm showing you, this is my nucleophile, just like this was my nucleophile. Here's my substrate. This was my substrate. And what's going to happen is the nucleophile is going to attack the electrophile. I need to form a bond between O and C, between my nucleophile and my carbon. Right? So this O needs to get past these hydrogens, right? I'm forming that bond and this guy leaves. So that's my single step reaction. See, now these guys inverted, right? They get pushed over like an umbrella being popped over. So this is why we see inversion of stereochemistry. You could think of it as that maybe this was, if this was a stereo center, right? We could say this guy's S and now this guy's R. There's inversion of stereochemistry. All right. It may not be inversion of absolute chemistry, but it is inversion of stereochemistry. What would happen now if I had methyls here? And my bromide. Here comes my hydroxide. What effect does it have by putting these methyls here, taking up much more space? There's more sterics there, right? This guy, this hydroxide, needs to attack. Come on, thing. Needs to get to this carbon, right? But now he's got to get past these bigger groups. So in this case, methyl substrates are best. Secondary and tertiary substrates are worse. So SN2 likes methyl primary substrates. SN1 forms a carbocation intermediate, likes what I said, likes tertiary carbocations. So here's a quick summary of this, and we'll talk more about this. But SN1, these are the important things you need to know. It's first order in the substrate only, right? Increasing the nucleophile concentration doesn't affect the rate. It's a two-step reaction. In the first rate-limiting step, you form a carbocation intermediate, and because that carbocation is planar, the nucleophile can add top to the bottom, and you get a racemic mixture of products. SN2 is second order. Both the substrate and the nucleophile have to smash into each other. Single-step reaction, and there's backside attack of the nucleophile with inversion of stereochemistry. So if we started with S, we could go to R. Whereas here, if we started with S, we'd get both R and S, a racemic mixture. So looking at these two pictures that I stole from masteringchemistry.com, very nice site, you should go there. Which one represents SN1 and which represents SN2? Right, in this case, we have a passive nucleophile kitty, right? He waits until, in this case, the OH, right, the OH2 plus leaves, leaving the carbocation intermediate, and then he adds in this two-step reaction. In the one-step reaction, aggressive kitty, right, he's the nucleophile. He does backside attack, and sleeping kitty leaves all in one step, right? So this represents SN2, this represents SN1. All right, and like I said, these are really fundamental reactions in organic chemistry. They show up a lot, and they're really good for thinking about different organic concepts. So we'll think more about those.